Okay, so I just proved to you that for every non-deterministic finite automaton, there is an equivalent deterministic finite automaton, and as a result of that very important theorem, we have now a corollary, a simpler theorem that we can now prove much faster and easier, and that is that we call it corollary 1.40, and it states that a language is regular if and only if some non-deterministic finite automaton recognizes it. Now, this is very important because and this is what I talked about earlier, that the idea that non-deterministic finite automata and deterministic ones are equivalent. This statement is very powerful, because if we show that NFAs and DFAs are equal, and because we defined a regular language being a language that is accepted or recognized by a DFA, therefore a regular language is regular if an NFA recognizes it, and vice versa. Now, this corollary actually is two statements in one statement. Notice the if and only if statement here. It's basically a bidirectional implication. It states that a language is regular, or rather, if a language is regular, then an NFA recognizes it. And backwards, it say if an NFA recognizes a language, then that language is regular. So we have to prove both directions. So the if direction. The if direction says that if some NFA recognizes a language, then that language is regular. From the theorem we proved earlier, we know that an NFA can be converted into a DFA, and so if an NFA recognizes a language, then the DFA that will be constructed on it is going to recognize that language as a result of the theorem that we saw earlier, and that DFA recognizes this language, and by definition then that language must be regular. So that proves the forward direction. The reverse direction, or the only if direction, states that if a language is regular, then an NFA recognizes it. We say that from the definition earlier that a language is regular if some DFA recognizes it. That's by definition. Also, we know that NFAs are generalizations of DFA, so every DFA is an NFA. So this proves the second direction. This proves that if a language is regular, some DFA recognizes it, and the DFA is NFA, therefore some NFA recognizes it, and it proves the other way of or the reverse direction of our implication. So by this proof, then we prove the corollary that a language is regular if some NFA recognizes it, or if some NFA recognizes a language, then that language must be regular. So, great news and great information, rather very powerful stuff for us so far. And before we go to the closure properties that we will actually show in the next unit, closure properties of regular operations, I would like to show you a conversion process. The conversion process as a result of our theorem of the equivalence of NFAs and DFAs. We take the NFA n sub 4 that we saw earlier. It's made of 3 states, q sub 1, q sub 2, q sub 3, and it also has an epsilon transition. We will convert this into a DFA, and we'll show that DFA will have 2 to the n states, in fact 8 states, and then we'll see that we can simplify it into a smaller DFA with 6 states, but that would be the smallest DFA for this language with 6 states. So let's go ahead and start working on this conversion. Okay, so my NFA n sub 4, I called it, is a 5-tuple, and its q is q sub 1, q sub 2, and q sub 3. In fact, actually, let's simplify this. Let's just call these 1, 2, and 3. So, because it's going to be just a lot of letters there. So this machine is made of 3 states. So the Q of my NFA is 1, 2, and 3. Its alphabet is A and B. It has a delta function. Its start state is 1, and its accept state is set 1. So that is my NFA. I want to construct a DFA for it that is Q prime sigma delta prime Q sub 0 and F prime. So now let's start working on this. The first thing, I know that 1, Q prime of my DFA is the power set of Q. Therefore, it is going to be equal to set of empty set 1, set 2, set 3, and then set 1, 2, set 1, 3, set 2, 3, and finally set 1, 2, 3. Okay, so each of these are now the members. So remember when I said R would be these guys. So R being a member of Q prime. Let me be a little bit neater here, because we need to be neat when we are working with these sets in sets in sets in sets. So R is a member of Q prime. So R is composed of sets itself. Okay, so then 2, I know that sigma is equal to A and B, which is nothing really impressive about it at this point. Then 3, delta prime will be from Q prime cross sigma epsilon, which means that then sigma epsilon here is going to be sigma union with epsilon over into Q prime. So the inputs of my delta is going to be a set of states and an alphabet symbol. And then the result is going to be a set of states. So that's what I know that the delta prime is capable of. And so then as a result of my computation earlier, I know that the delta prime of R and A for some, actually let me write this down again for you so we will be easily recognizing it. So for every R from Q prime and A from your alphabet, then the delta prime of R and A is going to be the union of every member of R if it's passed to the delta. Actually, I forgot the E, epsilon arrows. So it would be every state that is reachable along epsilon transitions, 0 or more epsilon transitions of delta if I pass R and A to it. So this is going to be union of those guys. Okay, so so that's that. For the Q sub prime 0 is going to be every state that is reachable from the start state of my NFA along 0 or more epsilon transitions. And finally, F prime will be all states Q, actually R from Q prime. So it would be a set of a set R from Q prime such that R union F is not empty. or that R contains at least one of the except states of my original um, uh, original NFA. So now let's go ahead and build this guy and see how it works. First thing, I'm going to go actually and write down again the transition function of my NFA. So for 0, for 1, and for epsilon, 1, 2, and 3. So 1 for A, well actually it was A and B. So 1 over an A goes to nothing, over B goes to set 2, over epsilon goes to set 3, then 2 over A goes to 2 and 3, over with B goes to set 3, and over with epsilon goes nowhere, and 3 with A goes to 1, with 2 with B doesn't go anywhere, and with epsilon doesn't go anywhere. So that is the original delta. Okay, so now what I need to do is to create the delta prime, the Q prime, and the F prime, because I already have the Q prime here, and I also have the sigma. So let's work with the delta prime and see how the delta prime would look like. So the delta prime is a function that has effectively 8 inputs. Remember, delta prime is from Q prime cross sigma epsilon over to Q prime. And I'm actually recognizing the epsilon here with the E. So this takes care of epsilon. So I don't have to put that in the output arrow. So I'm going to basically use A and B. And so my input states are going to be from Q prime, and Q prime is phi, and then set 1, set 2, set 3, set 1, 2, 1, 3, 2, 3, and 1, 2, 3. So it's going to be phi, set 1, set 2, set 3, set 1, 2, set 1, 3, set 2, 3, and set 1, 2, and 3. Okay, now let's see what's going to happen from the delta prime. So the delta prime basically takes each of these states, and so we call each of these R. Okay, and then each of them will have a member. For each member of that set, we'll pass that member into delta. We'll see what it goes, and then we'll see what it goes after an epsilon arrow. And then that would be the set that we union together. So first off, let's see what happens with phi. So what's going to happen if if R is equal to phi, then R will be basically nothing, right? So we're going to see what happens if we pass phi into the delta prime. And so since we don't have any states in the delta prime with an empty state with empty transitions, so with both A and B, we're going to go to phi. So that's for the for if R was the empty state. Now what happens if R is set 1? What we're going to have to do is for every R from set 1, basically calculate the union of R if we pass, actually delta, if we pass 1 and A to it, and then see what that transition goes to. And then see what epsilon or rather what epsilon arrows take us from there. So if you look at 1 and A, you notice that state 1 with A doesn't have any transitions, so it goes to phi, and then state phi doesn't have any epsilon transition, so it doesn't go anywhere. So 1 and A will go to the state with the empty states. Now, so that's for A. Now let's see what's going to happen with B, right? So with B, state 1 with B goes to state 2, right? And so therefore, the delta prime here is going to be state 2. Okay. Now notice for these three guys, you have one member. So we really don't have any. Actually, my spelling is bad. Any unioning for these guys. These first four actually are going to be really quick. So then let's see what happens if R is state 2. Then we'll do for R belonging to state 2, which means that then in this case R is equal to 2. Then delta prime of 2 and A is going to be E of delta of 2 and A. Okay, so if you are in state 2 with A, you are going to stay in 2 or 3. So here you're going to be in 2 and 3, and none of those have any epsilon transitions that go out go out to any additional states. So 2 with A goes to state 2, 3. So state 2 with A goes to state 2, 3. How about for B? When the letter is B, what happens for it? So then delta prime of state 2 and B is effectively equal to E of delta of 2 and B. Now, delta of 2 and B goes to state 3, and then there's no outgoing transitions for epsilon, so it's going to stay in. It's going to transition into set 3. How about 3? So what if now if R is equal to set 3, then delta prime of set 3 and A is going to be epsilon transitions after the delta of 3 and A. So delta of 3 and A goes to 1. So this is nice then. See, delta of 3 and A, this guy is going to go to 1. And then 1 over an epsilon arrow is going to go to 3. So in total, this guy is going to be set 1, 3. Because, see, when you are in state 3 and you take A, you go to state 1. And you follow the transition epsilon, you go back to state 3. So effectively, the E of delta 3 and A is going to be state 1 and 3. So this guy then is going to be state 1, 3. You first perform the transition, then add any additional reachable states over epsilon. And that takes care of that process. What's going to happen with B? If this state is A, is state set 3, the delta prime of set 3 and B is going to be equal to E of delta of 3 and B. Now this guy is empty. This whole thing is going to be empty. So we're going to go to the empty set. Okay, wonderful. We took care of all the states that were made of one original state. Now, we need to do the two states here. So now these guys, if you look at these guys, R has 2 members. Now the union comes in handy. So what if R is equal to state 1, 2? What is going to be then for A? Delta prime of state 1, 2 for A. Remember, this is going to be union of R belonging to small r belonging to the states that you have here. So R1, 2 of E of delta of R and A. Okay. Now, since we have two sets, then it's going to be E of delta of 1 and A union with this. Let me just clean up a little here. Okay, so this is going to be that guy. So you're going to get this union with, and then E of delta of 2 and A. Now you see you have two deltas then you need to process, one for 1 and one for 2. So we know that E of delta of 1 and A was E of delta of 1 and A was phi, and then so this guy is going to be phi, and then we know E of delta of 2 and A, we already calculated it here, so that's 2 and 3. So that would be 2 and 3 there. So then this guy is going to be set 2 and 3, and then so therefore here I have the union of phi and 2 comma 3 set, which would be set 2 comma 3. So then 1 comma 2 goes to 2 comma 3 for A. Then how about for B? What would be the delta prime of 1 comma 2 for B? It would be the union again of R being a member of 1, 2 delta of R and A, which will be E of delta of 1 and B union with E of delta of 2 and B. Okay, so E of 1 and B is 2, so that this guy is set 2, and E of delta of 2 and B is 3, so this guy is set 3. So we're going to get set 2 union with set 3, which will be union set 2 comma 3. So this guy is going to go to 2 comma 3 as well. In fact, let me actually move these guys a little bit closer to get some room. Well, it should be good. So we keep going. So then for E of 1, 3, so I'm going to have to calculate E of 1, 3. So if R is equal to set 1 comma 3, then for A I have delta prime of 1 comma 3, and A is equal to E of delta of 1 and A union with E of delta of 3 and A. So this guy is a phi, this guy, which is delta of 3 and A. Let's make it better. Delta of 3 and A. So delta of 3 and A is 1, 3. Set 1, 3. So this guy is going to go to set 1, 3. And then for B, delta prime of set 1, 3 and B is going to be the union of E of delta of 1 and B with E of delta of 2 and B. Okay, so I know that this 1 and B is 2, so that's set 2, and 3 and B is phi, so that's phi, therefore this is going to be set 2. Okay, so I did 1, 2, 1, 3, and now all I'm left is with the delta of 2, 3, delta prime of 2 3 over A, and the delta prime of 2, 3 over B. So this is going to be E of each of them. Delta of 2 and A union with E of delta of 3 and A. So this guy, delta of 2 and A, which is this one, so that's going to be 2 and 3. And then 3 and A, which is this one, this guy is going to be 1 and 3. So when I union these, it's going to be 1, 2, and 3. Okay, so then this guy is going to be 1, 2, and 3. And with the B, I'm going to be basically doing the same thing, delta of 2 and B union with delta of 3 and B, which is going to be delta of 2 and B is 3, delta of 3 and B is 5, so the union of set 3 and empty set is going to be set 3. So this set is going to be set 3. Okay, now finally I will have to do the delta prime of 1, 2, and 3 for A, which is going to be the union of E of delta of 1 and A with delta of 2 and A with E of delta of 3 and A, unioning these three sets. So that set 1 and A is phi, this set 2 and A is 2 and 3, and the last set here 3 and A is 1 and 3. And therefore this is going to be union of phi with 2, 3 with 1, 3, which is going to be set 1, 2, 3. So this set is going to be 1, 2, 3. And then delta prime of set 1, 2, 3 with B is going to be the union of E of delta of 1 and B with E of delta of 2 and B with E of delta of 3 and B. So the first one, delta of 1 and B is 2, so it's going to be set 2. Delta of 2 and B is going to be set 3, so this is going to be union with set 3. And delta of 3 and B is set phi, so this will yield set 2 and 3. And so here is my my transition table. Basically what I did is that I listed all of the sets in the power set of my NFA states. Then for each symbol I basically went through and calculated the union of the transitions of my NFA for each symbol for each member of the set. And then also after I did the transition, I saw if there were any outgoing transitions over rather epsilon transitions, and these epsilon transitions I represented them by taking the epsilon arrows for the E's. And so this is it. So what I'm going to do next is I'm going to go ahead then draw the DFA for this language next, after we did all these transitions. I forgot one of the important parts here, and the Q sub let me actually change my color here. So Q sub 0 is going to be E of Q sub 0, which is going to be E of 1. So here step 4 is going to be Q prime 0 is going to be E of parenthesis 1. okay, which means that all the states that are reachable by 1. So I'm in 1, and then in 1 with epsilon, I go to 3. So this is going to be 1 comma 3. So that's my start state. So this guy is going to be my start state. And then finally, the F is going to be the set of all states that have 1 in them, which means that it's going to be, so this guy is going to be an accept state because it has 1. This guy is going to be an accept state. This guy is going to be an accept state. And this guy is going to be an accept state. So F is going to be set 1, set 1 comma 2, set 1 comma 3, and set 1 comma 2 comma 3. So it is going to be all the R's, which is these guys, that have some members of F, and F was 1. So 1, 1, 2, 1, 3, and 2, 3 is going to be my accept states. So next I'm going to draw the diagram for this and simplify the diagram, and that should be a very good case for the conversion. Okay, so now that we created our diagram, rather transition table for our automaton, the DFA, let's go ahead and make it. So I'm going to use the red color. It's going to be a bit better to see it. So I know that the start state of my machine, by looking at the calculations that I made, was effectively, if you remember, Q sub 0 prime was the set 1 comma 3, or the set that contained the start state of my NFA and any other state that could be reached from it by any epsilon transitions. So it could contain 1 and 3. So the set 1 comma 3 is my start state. Okay, so that's this set here. You could, when I'm drawing this, I could go either way. I could start from phi and then go down, or it may be a little bit easier to see if I just go along the start state and then go along each of the transitions and keep writing them and see what's going to happen with them. So let's start with the start state 1 comma 3 and see where we go with an A transition or a B transition. So I'm going to create an A transition. And so along the A transition, I'm going to transition into state. Actually, along the A transitions, I'm going to stay in itself, right? A transition is going to stay. And then along the B transition, I'm going to go to state set 2, right? So along the B transitions, I'm going to go and transition into state set 2. Okay, then let's look at the state set 2. With A transition, I'm going to go to state 2, 3, and then with B transition, I'm going to go to state 3. So from state 2, along the A transition, I'm going to make an A transition and a B transition. So then these happen. So for a B transition, we'll go to state 3, set 3, and then for A transition, we are going to go to state 2 comma 3. Okay, then let's take a look at state 3. So with state 3, for A, we go to state 1, 3. So for A, we go back to state 1 comma 3. We're in A transition from state 3. And then for B, we go to state phi. Then let's look at state phi. State phi with A and B goes to itself. So it's going to stay in phi with A and B. So for this, now for state 1, 3, I have a transition for A and B. For state 2, I have transition for A and B. For state 3, I have a transition for A and B. For state 5, I have a transition for A and B. And now we'll do state 2 and 3. So state 2 and 3 with a B transition goes to state 3. And then with an A transition, it goes to state 1, 2, 3. So along an A transition, you go to a new state called 1, 2, 3. And then with a B transition here, you go back. To 2 and 3, and with the A transition from that state, you stay in 2 and 3. So let's see which states we have done so far. We have done states 1, 3, which is, I'm going to just draw a green line and underneath them. Oops, let's actually draw a line through them. So I did state 1 and 3, then state 2, I did there, state 3, I did that, oops, I did that there, and then state 5, which will be there, state 2, 3, which is this, and state 1, 2, 3, which is this. Now notice that there are two states here, states 1 and 2, and states 1 and state 1. These two states are not reachable by any state in my machine. So state 1 effectively goes from, let me actually draw it here. So state 1 over with A goes to phi, and over with B goes to state 2. So I'm going to actually kind of draw it wiggly. And so that's that state. And for these, I'm going to draw a gray line on them. So these are not reachable. Okay. Actually, I probably should have drawn these with gray too. With A, with B, this guy is gonna go there. So state 1 and state 1, 2. State 1, 2, which goes to 2, 3 for both A and B transitions. And so if you look at these two states, state 1 and state 1, 2, they have outgoing transitions but no incoming transitions. That's why we couldn't reach them from the input states. So these two states basically and effectively become not reachable from 1, 3, which is your start state. And so as a result, these two states can be effectively ignored because if you start in state Q 1, 3, set 1, 3, those states 1 and 1, 2 are not going to be reached. So you could, as you see, the maximum number of states that a DFA equivalent to an NFA can have is going to be 2 to the n, if n was the number of states in the NFA. But it may have less states needed, as you have seen here, and effectively some of the states can be ignored, and you can create a simplified version. Okay, so I hope you enjoyed this learning unit, and this learning unit will have, and as you have seen so far, it's got 4 videos on it that you have seen, and this unit was dealing with the non-determinism as a means for creating flexible computation that we saw. If you have the Schweizer's book, the contents that we covered have been pages 48 to 58. Effectively started with non-determinism, went through a couple of examples, and saw how a non-deterministic finite automaton processes. Then we formally defined a non-deterministic finite automaton, and we proved a very, very important theorem in that the deterministic and non-deterministic finite automata are equivalent, and we saw an example of conversion. This gives us a very important tool in our toolbox of computation, non-deterministic finite automaton. And if you remember, when we were proving the closure properties of regular operations on regular languages, the set of regular languages, we could barely prove by construction that the union operation, the class of regular languages are closed under union, but we couldn't do anything with the FAs to prove the star operation or the concatenation operation. Now within NFAs, we will actually revisit the closure properties of regular operations, and we see that how we can prove that class of regular languages are closed under the union, the concatenation, and the star operations, and those will even enable us more to create even bigger languages, regular languages, from simpler ones. And then we'll continue our work with the definition of regular expressions and the equivalence of regular expressions with the automata. And so this is Unit 6 again. Please go ahead and study the contents of this book and try to go over all the examples that we've seen so far in the class and in the lecture videos, and also look at the next homework assignments that's posted on the Blackboard. And I will see you at Unit 7. Thank you.